Hello, everyone. My name is Gunnar Epping from Indiana University Bloomington, and I'll be presenting comparing Markov and quantum random walk models of categorization decisions. This is a pre-recorded presentation for the 2021 meeting of the Society for Mathematical Psychology. A number of experiments have demonstrated that there is a distinction between two different types of categorization tasks, those being rule-based tasks and information integration tasks. Our goal is to test whether we could distinguish between these two tasks by characterizing one using classical probability theory and the other using quantum probability theory. To give some background on rule-based and information integration categorization, rule-based categorization requires a verbalizable rule or some logical combination of verbalizable rules to correctly categorize stimuli. In the figure on the left, the rule would be something along the lines of, if the bar narrowness is above 7 cycles per disk, then the stimulus is a member of category A. And if the bar narrowness is below 7 cycles per disk, then the stimulus is a member of category B. When learning rule-based tasks, people are learning a decision bound between two categories. Since this learned decision bound is verbalizable, rule-based categorization is an explicit process where an observer uses executive attention to focus on a single relevant dimension while holding the rule in working memory to accurately categorize the stimulus. Information integration categorization requires the integration of multiple stimulus dimensions to correctly categorize stimuli and, unlike rule-based categorization, lacks a verbalizable rule to distinguish between categories. If you look at the figure on the left, the decision bound for the rule-based task is in units of cycle per disk, which is something that we can easily perceive and measure. But the information integration decision bound is in units of cycles per disk per degree, which isn't a measurable quantity. So, when learning information integration categories, people learn each category's structure and parameter space instead of learning a decision bound. This learning process is thought to be mediated by building stimulus-response associations. After successfully completing an information integration task, people are rarely able to describe their strategy. An example of this in the real world would be radiologists determining whether or not a tumor is present. Even after years of training, they're only partially successful at describing their categorization strategies. Since the categorization strategy is not verbalizable, information integration categorization is an implicit process that relies upon some internal evaluation of the stimulus. The fundamental difference between rule-based and information integration categorization is the necessity to focus on a single measurement quantity as opposed to simultaneous measurement of multiple quantities. There are many differences between classical and quantum probability theory, so I'll key in on a few here parts and overview other parts further in the presentation. Classical probability theory uses subsets of universal set to represent events, whereas quantum probability theory uses subspaces of a Hilbert space to represent events. In classical theory, all measurements of a system take place within a single sample space, that sample space being the universal set. According to the principle of complementarity in quantum theory, quantities or observables can be measured within a single sample space if they can be measured simultaneously with absolute certainty. Otherwise, a change of basis is required, which leads to measurements that do not commute. Below, you might recognize the first equation as Heisenberg's uncertainty principle, which places a lower bound on the mutual uncertainty for simultaneous measurements of a particle's position and momentum. The equation below that is the generalized uncertainty principle, which establishes a lower bound on the mutual uncertainty of any two observables. As you can see from the bottom equation, the degree to which two measurements do not commute with each other, or rather, the amount one measurement interferes with the other, determines the lower bound on the mutual uncertainty. Since all measurements commute in classical theory, there is no analog to this uncertainty minimum. Moving on to Markov versus quantum random walks of evidence accumulation. In a Markov random walk, a person's evidence state is theorized to be located in a definite single state. Markov walks operate on probabilities. With that in mind, the probability of the evidence state is updated by the transition operator, which maps the probability distribution across states from one time point to another. In the Markov random walk, uncertainty is treated as the modeler's uncertainty about the position of the person's evidence state. So, under this assumption, performing a measurement reads out the participant's evidence state without altering the system. Therefore, in this context, a categorization decision from a Markov random walk is an explicit readout of a person's belief about the stimulus's category. In a quantum random walk, the evidence state can be spread out over a superposition of states. And instead of operating on probabilities, a quantum walk operates on probability amplitudes. The amplitude of the evidence state is updated by the unitary operator, which maps the amplitude distribution across states from one time point to another. In the quantum random walk, uncertainty is treated as the participant's uncertainty rather than the modeler's uncertainty of the position of their evidence state. So, performing a measurement alters the state by probabilistically projecting the indefinite state onto the subspace spanned by the measurement operator. Therefore, in this context, a categorization decision from a quantum random walk is an implicit construction of a person's belief about the stimulus's category. Since rule-based measurements take place within a single sample space, and the evidence for one category or another accumulates using an explicit strategy, we assert that rule-based categorization decisions are characterized by classical probability theory using a Markov random walk process. Since information integration measurements occur simultaneously on multiple quantities, and evidence for one category or another accumulates using an implicit strategy, we assert that information integration categorization decisions are governed by quantum probability theory using a quantum random walk process, with the amount of mutual uncertainty between the two measurements being determined by the degree to which they interfere with one another. We believe the amount of category overlap modulates the degree to which information integration categorization decisions interfere with each other. Moving on to the experimental design. The stimuli that were used in this experiment were circular sine wave gratings that vary both on spatial frequency and orientation, like the one in the bottom left, and the same 50 stimuli were used on each participant in each task. The two categories had the exact same number of stimuli, variance on each stimulus dimension, and covariance between the two stimulus dimensions. The categories used in the information integration task were overlapping information integration categories, and the categories used in the rule-based task were 45-degree rotations of those categories. The information integration categories are displayed in the center, and the rule-based categories are displayed on the right. For both tasks, the experiment had two phases, an acquisition phase and a transfer phase. During the acquisition phase, people learned to categorize stimuli as either members of category K or category S. This phase consisted of up to 7 blocks with 50 trials per block. People had up to 5 seconds to respond on each trial, and feedback was provided after their response. During the transfer phase, people completed the study exclusively in one of two conditions, K then S or S then K. In condition K then S, people would first rate the likelihood on a scale of 0 to 5 that the presented stimulus belonged to category K, and subsequently, without altering the stimulus on the screen, rate the likelihood on a scale of 0 to 5 that the same stimulus belonged to category S. The same procedure applied to the S then K condition, just with the order of category ratings switched. The transfer phase consisted of 1 block and 50 trials, where each pair of ratings counted as a trial. Since we used overlapping categories in the information integration task, we expected to find significant order effects in the likelihood ratings and for the quantum model to outperform the Markov model. But in the rule-based task, we did not expect to find significant order effects in the likelihood ratings and expected for the quantum model and Markov model to perform similarly. Both Markov and quantum models used 96 evidence states. 96 was chosen because it's a multiple of 6. That way, each of the 6 possible ratings occupy the same number of evidence states, and because 96 is large enough to approximate a continuum. To generate probabilities for each process, 6 projection operators were used. Each of the projection operators pick out the probabilities that correspond to each rating. These are the projectors here on the right. Note, all off-diagonal elements of the projection operators are 0. The initial evidence state begins uniformly distributed across the 2 center ratings, 2 and 3, which correspond to the middle 32 evidence states. In the Markov model, the initial state is a distribution of probabilities, which is shown below, and in the quantum model, the initial distribution is a distribution of probability amplitudes. To evolve the state in the discrete state continuous time Markov random walk, we need to find the generator matrix. The generator matrix uses 2 free parameters, one to determine the drift rate, V, and another to determine the diffusion rate, sigma. The transition operator is derived from the generator matrix by solving the Kolmogorov forward equation. Since we are not trying to model time in this current study, we absorb time into the two free parameters. Finally, the joint probability of a pair of ratings is determined by applying the transition operator and projector for the first likelihood rating to the initial state, and then applying the transition operator and projector for the second likelihood rating. And then the joint probability is equal to the sum of the residual probabilities. In a similar manner, a Hamiltonian matrix is needed to evolve the state in the quantum random walk. Like the generator matrix, the Hamiltonian matrix uses two free parameters, one to determine the drift rate, V, where K is the index of the diagonal element, and the other to determine the diffusion rate, sigma. The unitary operator is derived from the Hamiltonian matrix by solving the Schrödinger equation, where we again absorb time into the two free parameters. Note, in the Schrödinger equation, I here is the imaginary number I that is needed to make the operator, well, unitary. Conceptually, the joint probability of a pair of ratings is computed differently compared to the Markov case. The first unitary operator rotates the initial state into the basis of the first likelihood rating. Then after the first projection, the Hermitian conjugate of the first unitary operator rotates the state out of the basis of the first likelihood rating into a neutral one. And then the second unitary operator rotates the state into the basis of the second likelihood rating where the second projection takes place. And then the joint probability is equal to the sum of the squared magnitude of the residual probability amplitudes. For both models, we estimated the parameters separately for each category and each condition. So we have 4 generator matrices in the Markov model and 4 Hamiltonian matrices in the quantum model. Therefore, each random walk model was initially built with 8 free parameters. After analyzing the results of the experiment, we noticed that many participants would default to rating one response as 0 and the other as 5. To account for this behavior, we added 2 mixture parameters that encode the probability that the participants skipped over the judgment process, selecting either k equals 5 and s equals 0 or k equals 0 and s equals 5. With the addition of these 2 parameters, each random walk model used 10 free parameters. Because we expected to find the order effects within categories across conditions, our results are displayed in 2 sets of 4 6x6 tables, one table for each category in each condition, and one set for each task. To equate the tables, the distributions were normalized to 100 as frequencies. For time constraints, I need to move forward, but if you'd like to have a closer look at the joint frequencies, feel free to pause the video. To assess the presence of order effects for both tasks, we fit 2 other basic models to the joint distributions. The first one is a saturated model, which assumes a different joint distribution for each of the 4 tables. The second one is a pooled across order model, which assumes the same joint distribution applies to both category K tables and assumes the same joint distribution applies to both category S tables. Another model we fit as more of a baseline is a restricted model, which assumes that the same joint distribution applies to all 4 tables. Using a chi-squared test to evaluate the differences between the g-squared values of the saturated and pooled across order models, we found that in the rule-based categorization task, we cannot reject the pooled across order model in favor of the saturated model, which implies that we did not find significant order effects in the likelihood ratings. But in the information integration task, we can reject the pooled across order model in favor of the saturated model, which implies that we did find significant order effects in the likelihood ratings. Presented here are various model comparison statistics for the saturated, restricted, Markov, and quantum models. In the rule-based task, the Markov model narrowly outperformed the quantum model according to the R-squared statistic, but the quantum model outperformed the Markov according to the G-squared statistic. The information integration task, the quantum model notably outperformed the Markov model on both of those statistics. According to AIC and BIC, for both tasks, the best model was the restricted model, but the quantum model still does relatively well, especially on BIC. By rejecting the pooled across order model in favor of the saturated model, we found significant order effects in the joint distribution of responses for the information integration task, but not for the rule-based task. Also, for both tasks, our model comparison supports the quantum random walk model over the Markov random walk model. We believe the strength of the quantum model is that it changes bases between the 2 categorization decisions, whereas the Markov model lies on the same basis. Going forward, we plan on varying the degree of overlap as we believe the magnitude of the order effect is proportional to the amount of information integration category overlap. Thank you for listening to my presentation. I look forward to answering any questions you may have about the study.